Okay, so today, guys, we are starting the new unit on dynamics. Good news is that it builds on a lot of the things we did in the first unit. So there's still going to be some vector addition stuff, which you guys are good at. There's going to be some acceleration stuff, which you guys are good at. Okay, and then there's going to be some stuff from Science 10 that you did last year that's also not too terrible difficult, and that is law of conservation of energy, the whole EI equals EF roller coaster kind of question near the end of the unit. Okay, we don't even build on that at all. It's exactly the same as it was last year. So there's a fair amount of stuff that's kind of being applied to something else or is an exact repeat of something you've done before. Okay? Reminders. Okay, exam is on Thursday. You guys may begin early, right, at 12:05. Okay, I have given those instructions to my sub. They will be here at 12:05 to let you start. Okay, but once class is over, the test is over. Okay, there's no coming back to finish later or anything like that. Okay, so when class is over, the test is over. I don't think time's going to be a factor for you guys. I think you'll finish it no problem as long as you kind of stay focused. And then on Friday, we'll go over the tests, okay, in class. That will take the bulk of class. Whatever time we have left, we might talk about some more dynamic stuff. And then on Wednesday of the next week, when you guys come back after your 4-day weekend, we'll continue on with more Newton and Newton's laws stuff. Okay? So today, we're going to be working on Newton's first law, which, while part of rocket science, is and of itself not rocket science. In fact, it is probably one of the most obvious things you can possibly imagine. Okay? Newton's first law is summed up in one word, and that word is inertia. Right? Newton's first law says that this desk right here will stay right there, provided I don't do anything to it. Well, duh. Of course it's not going to do anything if I don't do anything to it. What would possibly cause it to move other than an earthquake causing the floor to crack open underneath it? Like really, what else could cause that thing to move at this point? Maybe a strong wind coming through a broken window, I don't know. Okay? But really, there's no reason for this thing to move. Okay? Because how many forces are acting on this desk right now? Gravity's acting on this desk.
Normal force?
And normal force. And in case you haven't heard that term before, normal force is part of Newton's third law, okay? And it is every action has an equal and opposite reaction. So right now, gravity is pulling the chair into the floor. And the floor is responding by pushing back upwards with an equal and opposite force. Therefore, all the forces, two of them, that are acting on the chair or the desk are balanced. There's no net force. There's no imbalance in the forces acting on the desk. Thus, it stays still. Does that make sense? Okay. The same would be true if I had like a curling rock on a perfectly frictionless sheet of ice, which, by the way, would make curling interesting, because it's not. Okay, but would make it interesting to watch if you had perfectly frictionless ice, because nobody would be able to stand. Okay, curling actually requires that there is a little bit of friction in the ice, otherwise the turns and the sweeping wouldn't do anything. Okay, but let's say I had a curling rock on perfectly frictionless ice. Once I got it in motion and it left my hand, would it ever change its velocity? Not until it hits something. Right? But its velocity would stay constant because there's no unbalanced forces acting on it. Okay? Gravity's pulling it into the ice. Normal force is acting up. That's balanced. There's no vertical forces. And since the ice is frictionless, there's nothing to slow it down. Okay? It would just go. If I had a really long sheet of ice, it would go and go and go and would never slow down. Okay? Curling depends on the fact that there is some friction in the ice and the rock does eventually stop. Okay? In fact, all of curling is dependent on the fact that you can change the friction that is present on ice. That's what the sweepers do. Okay? If you have a really good sweeper, okay, they can actually change and steer the direction of the rock. And not because they put their broom on it and like give it a push. Okay? If they sweep on one side of the rock, that side of the rock experiences less friction because they melt a little bit of the ice. If you've ever seen curling ice, it's got little bumps on it all over the place. And when you sweep it, you melt those and they get a thin layer of water on top of the ice. Well, that has less friction than being in contact with bare ice. So if you sweep on one side of the rock will turn the other way because there's more friction on that side and it'll pull it in that direction, change its velocity, okay? So in a Newton's first law situation, an object is going to do one of two things: not move, because all the forces are balanced, or move at a constant velocity, because all the forces are balanced. Okay? What determines which one happens is whether the object was in motion or not. Okay? An object at rest remains at rest. That's the first part of Newton's first law. An object in motion will stay in motion at a constant velocity until acted upon by an external unbalanced force. Okay, so the rock on the frictionless ice has no unbalanced forces, so it would travel until it met an unbalanced force. Okay, now the key part of that is constant velocity. Will an object moving according to Newton's first law be able to change direction? Velocity is a vector quantity. Okay, so if something is moving at a constant velocity, it's also moving in a straight line. Okay, you've experienced this if you've ever tried to take a corner, an icy corner, too fast. Okay, if you take an icy corner too fast, what do? You go straight. You follow Newton's first law because there is not sufficient friction to change your velocity. You just travel at a constant velocity. The same velocity you were at before you tried to turn. And after you panicked, slammed on the brakes, and cranked the wheel as hard as you could, which are, by the way, the two worst things to do in that situation. Okay? It's counterintuitive, but you actually want to get off the brake and not steer as hard, and that might provide enough friction to allow you to turn a little bit. Hopefully you knew that already if you have your driver's license. Okay? But of course our natural reaction is to pile on the brakes and crank the wheel as hard as we can. Okay? But it doesn't actually work. Right? So Newton's first law talks about what happens when there's no unbalanced force. Newton's first law is a big deal when it comes to safety. Okay? Especially automobile safety. All right? If you are in a car and you are not seat belted in, and the car hits something and stops suddenly, what do? You obey Newton's first law because it's a law and it's immutable. You will continue to travel at the speed you were traveling when the car stopped because you are not attached to the car by your seatbelt. Okay, that's why it's the law to wear your seatbelt. It protects you from Newton's first law. Okay. Okay, so it protects you from Newton's first law by applying a force to you, right? If your car stops, you hit the seatbelt, and the seatbelt stops you from going forward, okay, saving your life. Okay, if you're not belted in, the next thing to provide an unbalanced force to you are things that are hard and unpleasant. Okay, steering wheel, windshield, pavement, other vehicles, all of those are bad. Okay, seatbelts are good. Okay, and they will save your life. Okay, so Newton's first law can be a pretty big deal. Now, what if you were in space? If you were in space and you got into motion, how do you stop?
You need like another force to balance you out in the opposite vector, I guess.
Exactly. Okay, it's why EVA suits, spacesuits, okay, actually have little tiny jets on them. Okay, like this isn't science fiction. This is how we do this. They've got little maneuvering jets, or what we call RCS, reaction control systems, because they work on action-reaction, Newton's third law. Okay, so if I'm rotating this direction, so counterclockwise, and I want to stop rotating that way, I fire this jet to push the other way and slow me down. If I'm traveling forwards, I fire the jets that face forwards so that they push me backwards and slow me down. What if I'm out of jet fuel? I'm in real big trouble. Okay? Because flailing around in space does nothing. flailing around in the air basically does nothing, but in space it does even less, because space is a vacuum. If you push on the air has to push back, but it doesn't do very much. In space, it does even less. And in space, no one can hear you scream. It's true. Okay, there's no air to carry the sound. Okay, so if you're floating away and you don't have a radio, okay, your partner will just see you flailing. He won't hear you scream. Okay, now if he puts his faceplate up to yours, he'll hear the screaming because the sound will travel through the faceplate, and then he'll go like, shut up, and he'll push away, okay, because he doesn't want to hear you anymore. But yeah, you would just float away according to Newton's first law. That's a big deal. Okay, they want to always make sure they know exactly how much thruster fuel they have. It was crucial when we landed on the moon, which by the way we did. Okay, so when they wanted to actually land on the moon, they were using thrusters that pushed up to slow their descent. They came very close to exhausting a lot of the fuel and not having enough to lift off again. Okay? And not being able to overcome their own inertia as well as the gravity of the moon and get back into orbit. Okay? Lots of things that have to be considered. Okay, so what's meant by inertia? Inertia is the tendency of an object to continue doing what it was already doing, sitting still or moving at a constant velocity. Okay? It's what happens when there's no unbalanced or net force. Okay? Now, inertia is related to the mass of an object. You may have noticed this, but heavier things are harder to move. Okay? You football guys, okay? Like, who do you want to get hit by? The wide receiver or the lineman? I want to get hit by the wide receiver. They're usually a lot lighter. Okay? I want to get hit by them because they don't have as much inertia. If they're moving toward me at a constant velocity, I have a much better chance of changing their velocity more than they have a chance of changing mine. Okay? It's why you never see a skinny sumo wrestler. Okay? I don't know if you guys ever watched sumo wrestling, but I've never seen a skinny guy sumo wrestle. If they do, they lose a lot. Okay? Because the whole point of sumo wrestling is to push people around. Well, the bigger you are, the harder you are to push around. That's back to football. It's the reason why the linemen are usually the bigger guys. They're harder to move around. Their job is to protect the quarterback, okay, and not get moved. Okay? So it's better for them to be the bigger guys on the team. Okay? Same with sumo wrestling. A big person has more inertia. Their tendency to sit still is much greater than a smaller person's. Okay? So if I went into a sumo ring, okay, and decided I'm going to try and move that big guy, I could run at him for all I'm worth. I'd run into him and I'd just bounce off. Okay? And he would go, shoo fly. Okay? Because he would hardly even feel it because he has so much more inertia than me. Okay? So, on that note then, what's the most important safety feature in your car? Okay? Everyone goes to seatbelts, and seatbelts are very important, make no mistake. All cars have that. But there's something else that's even more important, and not all cars have it.
Brakes.
Okay, all cars have brakes. But they're also important.
Airbags.
Airbags are also important, but not all cars have them.
ABS.
Also important, all cars have it. Well, modern cars all have it. Okay, think about this. A collision between a smart car and a semi-truck. Who wins?
Semi-truck.
Yeah, make no mistake, in every collision there's a winner and a loser. Okay? The smart car is the loser there. What does it not have that the truck has? Lots of mass. Okay? Guys, what determines the winner and the loser in most collisions is mass. The more of it you have, the more inertia you have, the more it's going to take to change your inertia. So if I'm driving the semi-truck at 100 kilometers an hour, I have a lot of inertia. The smart car going the other direction at 100 kilometers an hour has considerably less inertia. So when we collide, their velocity is going to change a lot because they have less inertia than me. Their tendency to keep moving forwards at 100 kilometers an hour is far less than my tendency to keep moving forwards at 100 kilometers an hour. Okay? So when you're selecting your first vehicle, make mass a priority. It affects your fuel economy, make no mistake. Heavier vehicles are going to use more fuel. But I like to win. I'm very competitive. Okay? So even in a crash, I want to win. Especially in a crash, I want to win. Okay? Because I got kids. And you know, if they're in the car, I want to win because I want to show them how important winning is. And also because they'll be safe. Okay? And I say this from experience. Okay? We once got in a collision when we had a Ford Expedition. If you don't know cars, that's like the largest SUV that Ford makes. It's based on their truck. Okay? So we're driving through an intersection, and this person somehow doesn't see this giant SUV bearing down on them and turns left in front of us without the right of way. Okay? So we plow into them, and we pushed that little, I think it was a Ford Focus, so a small little sedan. We pushed that car right through the intersection, okay, and onto the other side. So we completed going through the intersection, pushing the other car along, right? That car, all the airbags went off, okay, car was crunched up, okay, and I had to replace the driver's side front headlight assembly, and my airbags didn't detonate. Okay, which meant that the acceleration we experienced wasn't even enough to detonate the airbags because we had more inertia. Okay? It had nothing to do with the fact that we were going 60 kilometers an hour, which was the speed limit, by the way. It was not speeding. Okay? And she was stationary. Okay? It was the fact that there's just more matter in our truck than there was in that little car. And our tendency to keep doing what we were doing, moving 60 kilometers per hour, was greater than hers standing still. Okay, that's why she was pushed through the intersections and her car experienced more damage than ours. Okay? So, something to consider. Bigger vehicle, chance to win more often. Okay, making sense? That's why a tank always wins. Okay, you just can't legally drive a tank on the road. Sometimes it's too bad.
It's kind of like unrelated, but do you think that it affect insurance, having like a bigger vehicle, cheaper insurance?
It doesn't, because I mean, you're still going to get damage, right? It doesn't really, from what I've noticed anyway. Like our smaller SUV, the insurance is significantly cheaper. I mean, there's lots of factors that affect insurance, but I haven't noticed that mass is one of them. Okay. So mass affects inertia. The more of it you have, the greater your tendency to continue doing what you were doing, okay? And to change your inertia means you have to apply force, okay? If I'm driving down the road and I see a stop sign coming, I apply the brakes. What force am I using? What force do your brakes use to slow you down?
Friction.
Friction, okay? So I use the force of friction to change my inertia. I will take it from moving forwards at a constant velocity to being stopped at the stop sign. Okay? A force is required anytime you want to change the velocity of an object and thus the object's inertia. Okay? All right. So, we have to understand what force means, because this whole unit is about forces, work, and energy. Right? A force is a push or a pull. Okay? Anything that can apply to an object and cause it to possibly move, okay, or change in velocity. Right? So a force is a push or a pull. Okay? Force is a vector quantity. When you push on something, you're pushing it in a certain direction, okay, or pulling it in a certain direction. If I grab the front of this desk, okay, I'd be pulling it, I don't know, approximately north, okay, so it would be however many newtons north. Newtons, by the way, are the units for force. Okay? Newton did a lot for physics, so we named the units for force after him. Okay? In the same way that the units for energy are named after Joule. Right? So if you do something great in physics, you get a unit named after you, or something like that. Okay? All right, force of gravity. Okay? Gravity applies a force. It's always changing the velocity of objects flying through the air. Okay? Bulldozer pushing down a wall. Okay? Tow truck pulling the car. Okay? In the example of the tow truck, the force is angled this way. Does that mean it has both a vertical and a horizontal component? It does. Okay? What would the vertical component, whoa, that's not what I drew. What would the vertical component of this force be equal but opposite to, assuming I'm just pulling the car horizontally? Force of gravity. Okay? Force of gravity would want to pull the car down. Force in the cable, the vertical component of it, would offset it so that the car doesn't move up or down. Okay? Now, if the truck is moving at a constant velocity, okay, this forward component from the truck would be offset by what would resist the movement?
Resistance.
Yeah, friction of all kinds, air resistance, rolling resistance, all of that. Okay, if this thing was moving at a constant velocity, the net force would be zero. There's lots of forces acting on this car, but they all balance out to zero if it's traveling at a constant velocity. Okay, they're all balanced. And that's the situation that Newton's first law applies to. Okay? All right, now I'm going to show you guys. All right, so as we saw, Woody floats away. He's got no way to change his inertia. He's just going to move at a constant velocity forever. Okay? In fact, we use that to take spacecraft to other planets. Okay? All of our little, like New Horizons and Voyager and all of those, they don't have the thrusters on the whole way there. They don't have nearly that much fuel. They get on course, shut the thrusters off, and coast. Okay? Newton's first law will allow them to get there. We just aim at a point in space where that planet is going to be, and then when we get there, we turn the engines back on and slow down. Okay? But most of the time, with space travel, you're just coasting along. Okay? Because there's nothing that's going to slow you down. Okay. Also, mass is a scalar quantity. Okay? When you tell someone the mass of something, you say, well, the mass of that is 20 kilograms. It's not 20 kilograms north. Okay? Mass is how much matter is in a certain object. So there's no vector on that. Mass is simply a scalar quantity. Okay? But here's a place where, in North American society especially, we mess up. We confuse mass and weight to be the same thing, and they are not. Okay? Mass is how much of you or how much matter is possessed by an object. How much is it made up of? Okay? Weight is a force. Weight is the force of gravity pulling you down. Okay? So mass is in kilograms. Okay? Weight is in newtons. Okay? I like to do this when people ask me, how much do you weigh? I tell them. I tell them I weigh 785 newtons. At which point they usually chuckle awkwardly and find someone else to talk to, which is a win. It's a double win for me. I'm not very social, and I didn't have to answer. It was really a rude question for them to ask anyway. Okay, so, and I told the truth. That's how much I weigh. That's how much gravity pulls on my mass. I didn't have to tell them my mass, and they probably didn't realize if they divided that number by 9.81, they'd have my mass in kilograms. Okay, that's for them to figure out. Okay, but your weight and your mass are different. Like, the best way to lose weight, go somewhere where gravity is less. Okay? If I go to the moon, I'll weigh 1/6 what I weigh here, but I'll still have a spare tire around the middle. Okay? I'll just weigh less because gravity doesn't pull as hard on the moon. Or if I go to the top of a really tall mountain and I get a little further away from the center of the earth, I'll weigh a little bit less. There'll still be just as much, well, maybe if I had to walk up to the top of the mountain, I might actually lose mass on the way up. But okay, if I took a helicopter to the top, there'll be just as much of me when I get up there. I'll just weigh a little bit less. Weight is dependent on gravity. I could go to Mars and weigh 1/3 of what I weigh here, but there'll be just as much of me. Okay, so we all use the term all the time. I got to lose some weight, or I got to put on some weight. No, you got to lose some mass or put on some mass. Okay, you got to make more or less of you, whichever is your focus. Okay, you're adding more or taking some away from you. Okay, you want to weigh less, just go somewhere where gravity doesn't pull on you as hard. Okay, that's the best way to lose weight. And you'll feel good too, because you'll weigh less. You'll be able to jump higher. Okay? You can go to the gym and look really cool, because you can put like 4 plates on the bar and just start going because it doesn't weigh as much. It's just as much mass. Okay? Now, on that note, do they lift weights on the International Space Station? They actually have a Bowflex. They lift weights. They use resistance. If you put a bench and a barbell and a bunch of plates on the International Space Station, you'll look cool for about a half a second. You can load that thing up with like 4 plates aside and go like this. And you'll be able to bench press that, no problem. But you won't be able to stop it. Because once it gets moving, off you go. Okay, you're just gonna go right along with it. Okay, because there's no gravity to stop it. Okay, once you give it some inertia, off it goes and you go with it because it probably weighs more than you do if you got 4 plates on each side of the bar. Okay, so they don't use weights on the International Space Station for 2 reasons. They're useless and it costs a lot of money to move weight to the International Space Station. It's literally like thousands of dollars a kilogram, okay, to get things up there. So they're kind of concerned with like food and water and other important supplies. All right, so as long as we understand this, weight and mass are 2 entirely different things. They're related, but they're entirely different, okay? Mass, how much of an object there is. Weight, how much does gravity pull on that mass? Now, when you lose mass, do you also lose weight? Yes, you do, okay? Provided you're here, okay? If you go on a diet and lose some weight, or you conversely, you hit the gym and you put on some weight, okay? You put on mass, or you lose mass. If you're staying here, you also change your weight because gravity hasn't changed, okay? But one is a force and the other is not. Force is a vector quantity. Okay? Usually when people ask me that question, I also say 785 newtons down. That really throws them. But it's also the truth. Gravity pulls me down. Okay? Stupid gravity, always pulling me down. Okay? So, something to think about. Weight and mass are 2 different things. Mass affects your inertia. Weight doesn't. Okay? Weight says you're going to go this way. All right. Okay, so Newton's first law, okay? Think of hockey, we used curling earlier, okay? If a player doesn't hit a stationary puck, it's just gonna sit there, okay? All the forces acting on the puck are balanced and it'll just sit there on the ice, okay? But if somebody comes in and one-times it, okay, they're going to exert a force on the puck and the puck is gonna change its velocity because there's a force acting on it, okay? How long will that puck accelerate for?
It doesn't accelerate. It decelerates, right?
After it leaves the stick, yes.
Yeah.
So it's only accelerating for,
1 moment.
yeah, for as long as the stick
Yeah.
is pushing on it, right? So when someone comes and winds up and takes a one-timer, that puck is only accelerating for as long as the stick is pushing on it. Once the puck leaves the stick, if it's perfectly frictionless ice and it's not and stays on the ice, it would travel at a constant velocity after that. Okay? But it's only actually accelerating for as long as the forces aren't balanced. That's as long as the stick is pushing on it. Okay? Everyone okay with that idea? Okay, so Newton's first law says that an object at rest will remain at rest. An object traveling at a constant speed, or constant velocity, it should say, will continue to do so unless acted upon by a net force. Guys, if I didn't change that in your notes, that does need to say velocity. Speed is wrong. Okay? You can be traveling at a constant speed, okay, and be accelerating. If you turn a corner, you can move at a constant speed, but your direction is changing, therefore you are accelerating. Scalar versus vector quantity. Okay, so a couple applications of that. Okay, if you have like a stack of like checkers or poker chips or something like that, and you make a stack and then you shoot one at the bottom of the stack. If you hit it right, you should be able to knock one out and the stack won't tip. Okay, why is that?
Inertia?
Yeah, the stack's inertia is to stay still, right? If you only make contact with the bottom of the stack, you'll only make contact with one of the chips, okay? And then theoretically it would stay put. Same with, has anyone ever tried the pull the tablecloth out from under the dishes trick? Okay, if you're gonna try that, go to the dollar store and buy a bunch of plastic dishes. Okay, do not put mom's best china on the table. Okay? And it also helps if you have a slippery tablecloth, like a cloth tablecloth is not gonna work. There's way too much friction there. If you get one of those like vinyl ones, okay, they slide pretty easily, right? Now, the key to pulling the tablecloth out is to A, do it quickly, and B, what direction should you pull it? Yeah, straight, or the best way is to push your hands kind of against the edge of the table and pull down. That way the tablecloth can only move horizontally. What's the mistake most people make? Then they pull upwards on the tablecloth, which creates a wave in the tablecloth and knocks everything over. Okay? The best way to do it is to use the edge of the table to make sure that the tablecloth can only slide towards you. Okay? Now, it also works better if all the dishes are heavy. Yeah, the heavier they are, the more likely they are to stay put because they have more inertia and more tendency to stay put. Okay? You thought it was magic, but it's not. It's all physics. Okay? They're just, the hand is quicker than the eye and the brain is smarter than yours. I don't know, it's something like that. Okay? So that's what we're looking at there. Does that one still work? It does, okay. Better stop the recording or I'll get a copyright violation. Okay, so we've got a book here in the middle. Force number 1 is pushing to the left with 20 newtons worth of force. Force number 2 is pushing to the right with 18 newtons of force. So we have a net force of 2 newtons to the left. What's that object going to do? Okay, I see a few people pointing to the left. Is it going to move to the left at a constant velocity or is it going to accelerate to the left? It's going to accelerate. Remember, something only moves at a constant velocity if the forces are balanced or equal, yeah. Okay, if there's no net force, in this case there is a net force, okay, that net force is going to cause an acceleration. That's the next thing that we're going to talk about, okay, when we talk about Newton's second law. Okay, so we talked about this, inertia and mass, okay, if we apply the same force, so let's say you've got, you're in the middle of the street for some reason, okay, and coming towards you is a kid on a tricycle moving at 20 kilometers per hour, so it's a fast tricycle, okay, at 20 kilometers per hour, and a bus moving towards you at 20 kilometers an hour. You can't get out of the way of both. You're going to get hit by one of them. Which one do you choose? The tricycle. Because you know what? You got a pretty good chance of stopping the kid on the tricycle. You can probably like reach out, grab the handlebars, and stop them. And even if you can't, they're not going to hurt you that bad because they don't have enough mass. They don't have enough inertia. You try that trick with the bus, unless you're a superhero, you're going to be a hood ornament, okay? Because it's not, they have too much mass, and you have no hope of changing it. Okay? If I'm out in space, and I'm next to the International Space Station, if I push on the International Space Station, will it move? It absolutely will. But I'll move more. Okay? That comes down to a Newton's third law thing. It has way more mass than me. Okay? We'll both move. There's a force being exerted, but my force will have very little effect on the space station, which has way more mass than I do. Okay? Okay. Now, I want to show you this, this stuff on crash tests, because inertia is based on mass, and we said mass is a very important safety feature. The more of it you have, okay, the less likely you are to get hurt. All of your car's safety systems work on the idea of keeping you in the car and reducing the amount of acceleration you experience. Okay, so the seat belt is mostly about keeping you in the car and not allowing Newton's first law to hurt you by having you exit the vehicle. Okay? Your airbag is actually more about Newton's second law. Hitting the airbag slows you down more slowly than hitting the steering wheel. Okay? And I say that coming from a generation where we didn't have airbags in every single car, okay? And most of the time in a car accident, everybody had the same injury. they got part of their scalp taken off. Okay? If you look at like people from your parents' generation or maybe your grandparents' generation, a lot of them will have the same scar if they were in a car accident. It's a little scar goes right along their scalp here because you go forward and hit the steering wheel. And at that time, the steering wheel was rigid. Okay? It was like one thin like piece of like metal or wood or whatever, and when you would hit it, it wouldn't cave in, it would just scalp you. Okay? Yeah. It was like you could get a pretty serious head injury, concussion, that kind of thing. Okay? Before airbags were prevalent, they actually had steering wheels that would collapse. If you hit them really hard, you could get them to cave in. Right? They were designed to do that, so when you came forward and hit it with your forehead, it would cave in, right? And you wouldn't get hurt as badly, and they were padded a little bit more. Airbags have taken out all of the need for that. Plus, your steering column usually breaks. In an accident, the whole part that your steering wheel is attached to will break and go forwards when you hit it. Okay? Also decreasing the rate at which you accelerate, which prevents injury. Okay? Your car's crumpling system, same thing. Okay? Your car, a modern car, is designed to destroy itself to save you. Okay? It has all the crumple zones. Okay? When it crumples, that takes longer to stop than if it hits something and doesn't change its shape. Okay? If it's rigid and just hits something, it stops immediately. But if it's got time to crumple, the crash takes longer. The acceleration is less. Okay? Comes back to this. This, that's what hurts you. Okay? How quickly you accelerate, that's what hurts you. Okay? So all of the crash systems in your car, even your seatbelt to an extent, but your airbags, the crumple zones, all of that stuff, are designed to make that number bigger. If that number is bigger, then you're dividing by a larger number and the acceleration is less. It's pretty simple physics. Okay? That part of it. Making the car do all those things is far more advanced engineering. Okay? Your brakes affect this part. Okay? Your brakes make that number hopefully smaller, because what's VF? Hopefully 0. If it's a negative number, you're really losing that collision because you're moving backwards. Okay? That happens in some collisions, as you'll see. Okay, so if you get in an accident, the pendulum will move forwards. And when it does, it lifts up the locking bar on its side, which then catches the ratcheted or toothed wheel that is part of where your seatbelt unravels from. Okay? So when it catches that, the seatbelt can't unravel anymore. Right? And there's no way for that to fail. If your car stops suddenly, you can't stop Newton's first law, the pendulum will swing forward and it will lock the seatbelt into the locked position so that you can't go forward. Now, modern seatbelts are a little tiny bit stretchy. You'd probably never notice it pulling on it, okay? But it will stretch a little bit. Okay? There's a tiny bit of give in it. Okay? If you get in a crash of more than 50 kilometers an hour and your car is in a write-off, okay, you would have to get the seatbelts replaced because they would stretch. Okay? So that's how the seatbelt works. Okay? When you move it quickly, you actually jerk the whole mechanism, which causes the whole thing. You usually pull up on the wheel a little bit, and it catches the locking bar. Okay? And that's why it won't unravel, okay, when you're in a hurry. Right? But that's how it works. It uses Newton's first law, okay, in order to save your life. Okay, one more video. I think we got time for it.